All right, good evening. My name is Hunter, and this is content review for general chemistry students. Our final week together, this is week 10, a little bit more on nuclear chemistry. Our first discussion point here is define the term half-life and illustrate it with an example. So radioactive half-life is simply the um, the time required for half of the atoms in a sample to decay. So let's go ahead and write that down. Half-life, sometimes written T sub 1/2, equals the time required for half of a sample to decay. The classic example is carbon-14. We use carbon-14 for a lot of processes in terms of dating mostly man-made objects, but you can go older. Um, Actually, I don't know if that's true, but I know when I was studying anthropology my first time around in college, we used carbon-14 dating a lot to determine the age of campsites and things like that. So carbon-14, written as C14, or you'll see it as C14 in notation like that, like we looked at last week. So the half-life of T14, or excuse me, of carbon-14 is 5770 years, 5,770 years. So after 5,770 years, a 10-gram sample would be reduced to 5 grams, or 50%, right? So with that knowledge and a couple of helpful equations, we're going to solve some more specific problems around this. So Pu-239 is a nuclear waste byproduct with a half-life of 24,000 years. What fraction of the Pu-239 present today will be present in 1,000 years? So we're going to take these equations, figure out first our decay constant, sometimes represented as lambda, sometimes represented as k. Either will work. And to do that, let's start with k equals ln of 2 over half-life. Ln of 2 is 0.693, and our half-life was 24,000 years. When we're dealing with time, just make sure that you keep your units consistent. We can do this in seconds, we can do it in minutes, we can do it in years, and so on. Just make sure that you do those conversions. Plug that into the calculator, and we should get 2.8875 times 10 to the negative 5 years. So it's not even going to take a year. It goes pretty quickly. So we've solved for our rate constant. And the reason we did that is because we need to plug it into this equation. Sometimes they make you memorize various equations for this, but all you need to know is that radioactive decay is a first order reaction. We have already looked at some first order reactions previously in your general chemistry studies. And so we're simply going to be putting our, this is our final amount of the isotope, and this is the initial amount. And because we're dealing with percentages, this initial amount can just be 1, or you can write it as 100%. Just make sure that you then also put this as a percentage and not a decimal. So let's go ahead and plug in some values. Natural log of our final amount of product equals, we've got negative k, I'm just rewriting the equation right now, times the amount of time elapsed plus the natural log of the initial amount. So again, the initial amount is 1. So ln of 1. ln of 1 is always 0, so we can actually nix that. We have our negative k constant, so negative 2.8875 times 10 to the negative 5 times the amount of time, which they gave us was 1,000 years, equals natural log of our final quantity. Now, to get rid of this natural log, you take e raised to the power of ln, and that will get rid of it. So we, in our calculator, type in, it's the second button, ln gives you e raised to the power of this quantity. And that is going to give us a final amount of 0.9715, or 97% of the original sample. Does this answer make sense? We have a half-life of 24,000 years. Much less than that has elapsed. Yeah, a sample size of 97% sounds about right. Okay. Next one, the isotope TL208 undergoes beta decay. Remember, beta decay is basically an electron with a half-life of 3.1 minutes, very, very fast. Question A, what isotope is produced by the decay? So this is a little bit of review from last week. We have our TL208. They gave us that. We need to go to our periodic table and look up how many protons are in the nucleus and determine the identity of TL. And that happens to be 81. We know that it undergoes beta decay. So we're basically getting, this is our beta electron, which has a charge of -1 and has no mass, functionally speaking, for our purposes. And then we sum across the top. We have 208 for our mass number. And then to have an electron on the product side, what do we have to do to the left side to balance that out? We would have to add a proton effectively. So we will call that 82. Then we have to go to our periodic table and find out what the identity of 82 is. And that happens to be lead. Plum bum. Okay, so our answer for A is lead 208. All right, next up, how long will it take for 99% of a sample of pure TL208 to decay? So this presents us with a couple problems. We are not given a decay constant, so we're going to have to solve for that again. We are given a half-life, so we can figure that out pretty easily. In fact, let's go ahead and do that. So our decay constant, I'm going to write it as lambda this time instead of k. That ln of 2 was 0.693 over the half-life is 3.1, and that was minutes. And plug and chug, that gives us, whoa, sorry about that, 0.2235. Okay, so now we can plug that into our first order kinematics equation. And I'm going to go ahead and write the whole thing out just to keep our stories straight. So we are solving for t. How long will it take? So I'm going to highlight that real quick. So we're solving for t. How long will it take for 99% of a pure sample? So we know that our initial is 1 and that the ln of 1 is always 0. So we've got that far. We know the final. We know that there's going to be 1% of that final left at the end of it. So ln of 0.01 equals our decay constant, the negative decay constant, times T. And I'm going to keep highlighting that T in red just so we can keep track of it. All right, ln of 0.01 is negative 4.6052. We've still got our constant there times T, and plus 0 we don't have to worry about. Okay. And simply divide the negative 0.2235 to get it out of there. And our final answer is T equals 20.6 minutes. Does this make sense? So with a half-life of, what did we say, 3.1 minutes, basically after 20 and a half minutes, a lot of half-lives will have happened already. And so with the first half-life, you end up with 50% of that sample. With the next half-life, you get with 50% of the remainder, and then on and on and on. So yeah, that makes sense. And question C was, what percentage of a pure TL208 sample remains undecayed after 1 hour? So undecayed, basically, that means that they're asking for what's left at the end. They're asking for this n sub t value. So keeping everything the same, let's go ahead and just move everything in. What percentage of pure sample remains after 1 hour? So keep your units consistent. We're given a half-life in minutes, and so we need to keep our t in minutes. So it's not 1, it's 60 minutes. There are 60 minutes in an hour. ln of 1 is always 0, so we don't have to worry about that. All right. Get rid of the ln. nt equals 1.5 times 10 to the 6. Let's go ahead and multiply that by 100%. Gives us 1.5 times 10 to the 4% of the original sample. Very, very, excuse me, -4. Very, very, very small sample. And that makes sense given our previous answer. After 20 and a half minutes, only 1% would be remaining. We're going 3 times longer than that, and we'll have a much, much, much smaller number. All right. Question 44. Isotopes such as aluminum-26, which has a half-life of 7.2 times 10 to the 5th years, this is very, very long, are believed to have been present in our solar system as it formed, but have since decayed and are now called extinct nucleotides. Question A. Aluminum-26 decays by positron emission or electron capture. So this is a review question. Write the equations for these two nuclear transformations. All right, so we're starting with aluminum 26. Go to our periodic table and remember that aluminum has 13 protons in its nucleus. Positron emission, we're emitting that positron. It has no mass, but it does have a 1 positive charge. And our product will have the same mass, excuse me, it's not aluminum. We'll have the same mass, 26 plus 0 is 0, 13 minus 1, because we've got 1 on the product side, 13 minus 1 would be 12. And what has 12 protons in its nucleus? Check your periodic table. That is not lead, that is magnesium. I had the previous question in my head, sorry. That is magnesium. Okay, so that's 1 done. Now let's look at electron capture. So same starting place. Electron capture, we're adding that electron or that beta particle. Captures that electron, so we're subtracting 1 from 13 again, gives us the same number of protons. There's no change in mass. Our answer again is magnesium 26. All right, so for part B, the Earth was formed about 4.7 times 10 to the ninth, so 4.7 billion years ago. How old was the Earth when 99.9999999 of the aluminum 26 originally present had decayed? So we're given a final amount, a final percentage, and we're going to say that the initial was 100%, and we know our half-life, so we need to solve for K in order to get to, K our decay constant, in order to get to a final amount, or not a final amount. We're solving for T. How old was the Earth? We're solving for T, the amount of time elapsed. I'm going to go ahead and write that equation down just so you can see it again. Negative decay constant times T plus ln initial, and we're solving for T. Really quick, we need to solve for lambda equals 0.693 over the half-life is 7.2 times 10 to the 5th years equals 9.625 times 10 to the negative 7 inverse years. And our final is 100 minus 99.999. What are there? 5 of those? 1, 2, 3, 4, 5. Yes. Okay. 6 nines. So that gives us 1 times 10 to the negative 6%. And I'm going to leave the units in there to help me remember that we're using percentage to solve this and not a decimal. Equals, we have our decay constant, that is 9.625 times 10 to the negative 7. And we're solving for time, plus ln of 100%. All right, so from left to right, ln of 1 times 10 to the negative 6 is negative 13.8155 equals negative 9.625 times 10 to the negative 7 t plus natural log of 100 is 4.605. All right, so to tidy this up, subtract negative 4.605 from both sides gives us negative 18.42 equals 9.625 times 10 to the negative 7t. Divide both sides by that. And we should get t equals 1.9. Negatives cancel out, so 1.9 times 10 to the 7 years. So 1.9, what was that, billion? No, not quite. So less than the total age of Earth, which makes sense because it's an extinct nuclide. Blissfully short problem set today. I want to thank you all again for your time and attention this term, and good luck on your finals. Have a blast this summer. I hope you enjoy the nice weather, and hopefully we get to see you in the future in our careers together.